All right, folks, let's get started. Boy, you're really obedient, aren't you? All right. This session has the subtitle, All You Ever Wanted to Know About the Statistics Behind Mplus, but We're Too Afraid to Ask. You might be sorry you asked. You're in for a wild ride where TMR is going to give you the deep statistical underpinnings behind this new version 8. TMR Asparohov has been with us at Mplus almost from the beginning. 17 years he's been with this effort. The program is now turning 19 years old, and a very sprightly 19-year-old. Lots of interesting developments in its future. I don't know if it's a he or a she. And TMR, we've been very fortunate to have him on the team. The team is very small, as you know. It's about 5 people full-time. And TMR is our resident genius. And he's the kind of guy who, when you get into a new area that he doesn't know anything about, he just jumps in and studies the literature, comes up to the research frontier of the topic, and then goes well beyond it, seemingly very easily too. So he's a great statistician. I used to try to influence him statistically in the beginning of our years together, but now it's he who influences me and teaches me. Just ask TMR is a standard line. So he's also a really great coder. So the programming, the algorithms come really natural to him. So with that, folks, TMR Asparohov.
Thank you. Thank you, Ben. So we'll get going. In this part 5, we're going to talk about the general DSEM model and the estimation method. I'm going to talk about methods for evaluating model fit using the DIC information criteria, and also using the estimated mean and variances. Then we're going to talk about centering. We'll talk about the mirror model that you heard a little bit about yesterday, measurement error autoregressive model. And the final topic will be adding covariates in the DSEM framework. And we'll also talk about the new model that we're working on, the residual DSEM model. That's going to be part of version 8.1. And this is basically kind of the paper that has all the details pretty much of this talk. So the general DSEM framework was designed to merge the time series, structure equation, and multi-level, and TVEM, time varying effect models. Those are basically the models that the coefficients, the regression and structural coefficients depend on time. So these four concepts are combined into a generalized framework in Mplus 8. The preset here is that we have these variables, dependent variables, YIT, eta IT, and XIT, and these are the dependent, latent, and covariates for individual I at time t. In such data, there are 4 distinct sources of correlations, and the DSEM framework actually allows you to parse out these correlations, figure out which one is which, evaluate them, determine them. And these correlations are as follows: the correlation due to individual specific effects, and that's basically taking care of the multi-level aspect of the model. Correlations due to proximity of observations, and that's basically the time series concept. Correlations between different variables, and that's the SEM part of the model. And correlations due to the same stage of evolution, which is the TVEM modeling framework. The DSEM model, as you heard already, it consists of actually 3 separate models: single-level model, 2-level model, and a cross-classified model. And in Mplus, you have to say 2-level to get the 2-level, type equals cross to get the cross-classified. We're going to talk about the cross-classified as being the most general model. And the model basically starts with this main decomposition equation here, basically, that decomposes a dependent variable into 3 separate components. This will be the individual contribution to that variable. This will be the time-specific contribution, and that's the residual. In Mplus terms, this will be basically the within-level component of the variable, the between cluster component of the variable, and the between time. So we have the 3 different, two separate between levels, and it's essentially a cross-classified model. So if you are familiar with the model that we had in version 7.5, which is a cross-classified model, that basically this is the fundamental equation that we used also there. And we separate the variable into these 3 variables. They're all latent. And for each of these 3 components, we built their own structure equations. This is the cross-classified model, and the 2-level and the single-level DSEM models, they're basically special case of this. And if you remove this component, the time-specific component, then you get the 2-level model. If you remove both this, the time-specific and the individual-specific component, then you get a single-level model. The cross-classified is the whole version. So the cross-classified is the most general model, but in reality, I'm going to talk about it just because, just to give you the most general model. But in reality, the cross-classified model is the hardest model to estimate. So just keep in mind some issues that are related to cross-classified models. So the cross-classified model actually requires that the time scale is aligned between individuals. So for example, it has to be something that time t for every individual means the same time t. So for example, second grade would mean that something happens in second grade for everybody. So if this is not, if the time scale is not aligned, and you have, for example, observational studies that time 1 really doesn't mean anything particular about it being time 1. It's just when you basically started observing the individual, then cross-classified model would generally not apply. So the cross-classified model doesn't apply for every application. So keep that in mind. The 2-level DSEM model is really has a simpler formulation, is the most common and introductory model for applications. So most probably your first DSEM application would be actually a 2-level model. The 2-level model also requires fewer time points. It can be estimated with fewer number of observations. So the requirements on the data set with 2-level models are smaller. The 2-level DSEM model is easier to estimate compared to the cross-classified because you just have much fewer number of random effects. In addition to that, something that's related to the current implementation in Mplus is that the cross-classified model can sometimes be very slow, in particular when you have subject-specific autoregressive coefficient and subject-specific variances. What happens in that case is that the structural equation models that you end up on the within level becomes so specific to the time and individual that for every time data point in your data set, you actually have to analyze a completely different structural equation model. So in those cases, the speed of the cross-classified DSEM model actually is much slower than the 2-level models. On the other hand, the 2-level DSEM models pretty much, regardless of what the model is, will actually give an acceptable speed for estimation. So one more issue here that I didn't mention is that, in terms of the requirements on the data set, in cross-classified models, actually, there is an additional issue about on the data, that not just the amount of points and the data, but also if it's particularly difficult to estimate cross-classified models with unbalanced designs, because remember that for each time point we estimate a time-specific effect. And when you have an unbalanced design, say a particular individual is observed for a very long time, then for these later points later points in time, you only have very few observations to estimate these time-specific effects. So generally, cross-classified models actually work better when you have, at each time point, you have multiple observations, so you can actually estimate well the random effects that are specific for this time. So here is basically, we are going to show you now the models for this. So this is the fundamental equation. We split the variables into these three parts, and each of these three variables is going to have its own structural model. And here's what the structural model looks for the within variable. So basically, it looks almost like a standard structural equation model. You have the dependent variables, and this is sort of what we call the measurement equation. You have the dependent variables measuring some latent factors. You can also regress the dependent variable on some on other dependent variables and covariates. The main difference between this is the structural equation, which is basically allows you to regress latent variables on other latent variables and also covariates. So the main difference between this equation and the standard structural equation model is the fact that we allow in the equation on the right-hand side to be all latent variables from the current period, but also from the previous L periods, where L is the lag of the model. So this is why we have this sum here, so that any latent variable that's in the previous L periods, so that's the index T minus L, can participate in this as predictor for the dependent variable in the current time point. One thing to note right off the bat here is that these predictors, when they're on the right-hand side, when you have y variables on the right-hand side, that is not actually the observed y, but it's the centered version. So on the within level, we never use the dependent variables are always centered. In other words, the contribution from the individual from the individual and the contribution from time are already removed, and so this is just the residual part. So these are centered versions. So this model basically is a combination of the state space model that has been the center of attention in the last few decades of dynamic structural modeling. It also combines the dynamic factor model, and then it merges this with the full SEM functionalities such as covariates, path analysis, regressions among latent variables, CFA, mimic models, correlated uniqueness. You also have lagged loadings that are, for the previous, the latent variables from the previous periods. And then in addition to this main generalization on the within level, we of course add the core extensions of two-level modeling, cross-classified modeling, as well as categorical variables. On level 2 and level 3, the individual level, the level for the individual effects, we just have the standard structural equation models, and same on the time-specific levels. And also note that here we can also use observed variables that are on these levels, such as time invariant individual level variables that are time invariant, or time specific variables that are individual invariant. And the same thing applies for covariates. And here also we have latent variables on the both levels. In this DSEM model, we also have on the within level, pretty much all the parameters can be random. So we have random intercepts, and generally, that's basically these fundamental components are sort of considered random intercepts. In addition to that, slopes can be random, loadings can be random, autoregressive parameters can be random, variances can be random now as well, as you heard yesterday, and that's basically a version 8 feature that's available not just for DSEM models, but also we implemented that for non-DSEM models with the Bayesian estimation. Random covariances, we discussed this quite a bit. We did not find an acceptable model that we were all agree on, and the reason we did not, they're technically not implemented. You can do what Ellen's example yesterday was showing, how to do random variances. You can introduce factors, common factors between variables, and then have those factors have subject-specific variances. So that's our way of actually having random covariances. But technically, we have not found another pure and easy model that would avoid this, the need for introducing an additional factor. So the reason we have not found an acceptable model is because we want to have a model that not just has a random covariance, but you can actually use the random effects in that yields the random covariances. We want to have these random effects on the between level. And that's a little tricky with random covariances, because when you have regressions on the between level, those things actually go out of bounds very easily. So it's not a straightforward thing to do. And there are models that would do it, but then they will be very difficult for you to interpret them. So we have not yet implemented that. So every random effect consists of two portions in the cross-classified framework. You can have it's basically an addition of an individual specific effect and a time specific effect. So when you introduce a random slope of some kind, you get actually two random slope, one on each of the two between levels. And those are assumed normally distributed random effects and are technically considered to be latent variables on those between levels. And so they're part of these vectors on level 2, latent vectors on level 2 and level 3. So this is basically the main decomposition for a random effect, for all the random effects except the random variances. So the random variances, we use a log normal distribution, where again, so the random variance is an exponent of the sum of these two random effects, one from each of the two levels. And of course, that's done to make sure that the variance stays always positive. So if you want to incorporate this capability that all these coefficients can be random, you can rewrite the equation on the within level model in a more general form. And so all of these parameters now have, you can actually add additional index to show that they actually vary they can vary also across individual and time. So all these coefficients can have these indices I and T. So that's a more general way to write the model. So the general assumption of the model is that all residual variables in the model, so all these variables here, those are assumed normal. So basically we state that as being conditional normality. Categorical variables are incorporated in the model using the underlying Y star approach. So it's basically a probit link function. And in these equations, we basically use Y star to incorporate categorical variables, which are subsequently cut through a threshold parameters. Missing data is also treated using likelihood approach. So under the missing at random assumption, the estimation guarantees consistent estimates. And the reason we say it's likelihood-based is because we use the MCMC estimation, which is likelihood-based, and asymptotically that guarantees consistent estimation. And I just to point out that these time series models, they have been, of course, in the econometrics literature for a very long time. But even for single-level models, having missing data in time series models is an innovation which is part of the DSEM framework. And missing data generally is not incorporated in these traditional econometrics approaches. So now we're going to turn attention to the RDSEM model. So this is again the model that we're working on now. So this is the residual DSEM model, and so the model is defined slightly differently. So the within level the within level model, the within level variables, so here the dependent and the latent variables on the within level model, they actually further split into two separate levels, which I called here the level 0 and the hat level. And the hat basically refers to the residual, and this would refer to the structural part, all the predictors. So we split it to show you what our DSEM model is. We basically have this additional, so the within level level is actually split into two separate levels. This level will contain the structural part of the variables, and this will be the autoregressive part of the variables. And we basically wanted to separate, there was a lot of interest in separating the predicting part of the equation from the autoregressive part of the equation. And so the equation now on the within level looks like that. So this, the level 0 part contains all these the prediction portion of the equation, and the autoregressive part of the equation is now separated. So basically all the hat variables here, they are regressed on each other, but they do not contain any of these prediction variables. And so basically the covariates are excluded from the autoregressive part of the equation. We will talk more about this in the examples. To specify completely this DSEM model, we also have to specify the initial conditions. So when we talk about these regression equations here, when you start the sequence, say at time t equals 1, you're going to get these variables that have negative indices and 0 indices. So you have to start somewhere. And there's different ways to do this, different approaches in the literature. But what we do in Mplus, we actually treat these parameters, these variables basically, that are with negative indices, we treat these as auxiliary parameters. They have their own prior. In general, these initial conditions, they're called initial conditions, they don't affect much of the model estimation as long as the time series is 50 points or more. Even with 20 points, probably the effect of this initial condition is very small. And basically the prior does not affect the results. However, for some small time series situations, these priors can have some minor effects. In Mplus, there are two options that are implemented, and the first option is the default option. It's something we do. We actually provide these priors for you, so you don't have to worry about them. So they're automatic priors, and we have this in the MCMC estimation. We have during the first 100 burn-in iterations, we update these priors of the initial conditions. What we do, so we start at standard normal priors for the initial conditions, and we keep iterating through the MCMC sequence, and at each iteration we update this prior to the sample quantities for each of the variables. So for example, to get the prior for eta with negative indices, after the first iterations those etas are imputed, and we compute the sample mean and the sample variance, and we set that to be the prior for the etas with the negative indices. And after the burn-in iterations, those burn-in iterations are discarded. They're not part of the iterations that we use to estimate the estimates of the model. So those are discarded, and that's necessary to make sure that the MCMC sequence that we use for the estimation is properly defined. So that's a very standard way of dealing with such issues. And this approach seems to be working quite well. And so we basically, I was working on this maybe more than a year ago, and pretty much nobody actually uses now anything but that at this point. It seems to work quite well in practice and even in simulation studies as well. The second approach, which is available to you and you can use it, is you can actually specify your own priors for these initial conditions in the model prior statement. And so the model prior statement generally is used to actually specify the priors for the model parameters. But now you can actually have, with DSEM models, you can also use actual variables from the model. So f is a factor here. You can use the variable from the model and specify a prior, and same thing for the dependent variable y here. And what that means, the interpretation of this is that you're specifying the priors for the initial conditions. But again, this is fairly tricky to use, especially when your variables are not standardized, and it's not even very straightforward to figure out what the proper mean should be in these situations. So generally, we don't recommend that we recommend that you use a default approach. So there's some features that are not available. We just kind of had to put an endpoint to actually release the program at some point. So those are not available, but they might be available in future versions. So non-recursive models are not available. That's actually generally for our base estimation. We don't have these models. This actually came up twice yesterday. So this is basically the lag zero regression coefficients between dependent variables. Those cannot be random at this point. Random loadings, currently they can be subject specific, but they cannot be time specific. They cannot have a time specific component. And we also don't have for categorical variables. The underlying y star, the lagged version of the underlying y star variable, that cannot be in the model. So the only way to actually do time series models with categorical variables is when they are used as measurement for a factor that has time series model. And that might actually be also resolved in the next one of the next versions of Mplus. So the DSEM estimation is, again, it's a Bayesian estimation. It's an MCMC estimation with the Gibbs sampler. We basically, the way the estimation works is we determine all the unknown quantities in the model. These are basically all latent variable, missing values, initial conditions, random effects, and the model parameters. And we split all these unknown quantities in the model into blocks. And we basically, in the Mplus estimation, these are the 13 blocks that we split the unknown quantities in, and those are basically the MCMC iteration basically updates each of these blocks using the conditional distribution that for each block we determine the conditional distribution of that block conditional on all other blocks, and as we iterate through the blocks, we basically update the quantity for each unknown value here. And we construct these distributions. As we keep iterating, we monitor the posterior distribution for each unknown quantity. Actually, we just monitor the model parameters. And as the a sequence progresses, it stabilizes, the distribution stabilizes, and we conclude that the sequence converges, and then we use this, the distribution that is being generated from the MCMC sequence to construct point estimate, standard errors, and so on. So the reason we actually use these 13 blocks, so that we have our strategy for actually estimating this is to we use some sort of a mini-max strategy. So we want to have the smallest amount of blocks that would allow us to have explicit posterior conditional distributions, so that we can easily generate values from the conditional distributions. We want these blocks to be as large as possible as to provide good mixing. So if there are quantities and non-quantities in the model that are highly correlated, those have to be grouped in the same blocks. Otherwise, we'll create this slow mixing that would actually make the convergence of the sequence very slow. So we basically want to have the smallest amount of blocks, but what that causes is, of course, that these are very large. These blocks become very large, and so the conditional distributions are very complex. More complex than if you just update one quantity at a time. But nevertheless, we want to have these big blocks to actually get a fast convergence. Once each block is determined, we actually split every block into subblocks that are, we find the smallest subblocks of elements that are independent, conditionally independent. So we actually generate from the smallest conditionally independent subblocks. So this is basically our strategy for the DSEM estimation and in general for our Bayes estimation. So there's some things. So for example, if you know how we estimate the two-level models in Mplus, so here's the individual level intercept, and also these are the slopes. In two-level, we actually, this is one block in two-level models. Now, in DSEM models, they're actually separated because of these centering issues, and the fact is that in DSEM models, this is not conditionally normal. The joint distribution of these two is not conditionally normal, so that's why they're separated. So it looks a little more complicated than the standard two-level model estimation. And there is another complexity, a little complication here. There's certain blocks in this set, so these are block 3, 6, and 7, that the posterior distribution is not, is actually, the conditional distribution is very large. So the conditional distribution of this term, which is basically the time-specific contribution conditional on all other blocks, it turns out that the size of that conditional distribution is the size of t. And we've made this algorithm to work with any size t, so that's not an acceptable situation. And therefore, what we have done is we actually split these blocks into time-specific blocks. And when we update this, we actually don't update the whole block as a whole, but that's actually representing these time-specific blocks. So Y3T would be updated sequentially as time increases. So, for example, at time, we first update the quantity at time equals 1, conditional on all the other times. Then we update the quantity at time equals 2, conditional on the time equals 1 and time equals 3 and so on. Then we move to point 3, update the quantity at time equals 3, conditional on the previous time points and the subsequent time points, of course, and we condition basically on the current quantities that are generated at these other known quantities. So this is kind of a little summary of what goes on. And you repeat cycling between the blocks to get this posterior distribution. And all these conditional distributions that are, so basically the MCMC estimation consists of essentially providing these 13 conditional distributions. Once you have these 13 conditional distributions, you let the MCMC sequence generate all the unknown quantities, and you get these parameter estimates. So as long as these 13 conditional distributions are correct, you get a correct estimation. So we move to the next topic, so evaluating model fit. And we have two methods for evaluating model fit, the DIC and using model estimated means and variances, comparison between model estimated means and variance and sample quantities. So let's look at the DIC criterion. So the DIC is based on this quantity. So theta represents here the unknown quantities in the model, so the parameters. And that's basically, it's called the deviance, is the log likelihood of the observed data, conditional on these unknown quantities. This PD is called the estimated number of parameters, and you can find that in the Mplus output. And it's essentially the average deviance across the MCMC iterations minus the deviance value at the average parameter estimates. And this basically quantity is supposed to approximate the number of parameters in the model. And then the DIC is just a simple combination of those two values, the deviance at the average parameters plus 2 times the number of estimated parameters. Despite this kind of simple and clear definition of the DIC, there's actually, DIC is a little tricky to use. And the reason is because, and that's actually applies also not just to DSEM models, but also in two-level models and other models. And the reason it's tricky to use is because it's not very clear what people use for theta. So what is actually considered a non-parameter in this model? So for example, in the MCMC estimation, missing values of observed variables can be considered or not the non-parameters. So those theta parameters can include these missing values, or if you, depending on how you define it, they might not include the missing values. And same thing applies for latent variables. So the theta may or may not include latent variables. And to actually understand what DIC, what is the meaning of DIC, you have to understand the list, what exactly goes into this theta parameter. And the reason you have to know what goes into the theta parameter is because otherwise you cannot, you basically, for the same model, you can actually compute two different versions of the DIC depending on what you actually consider non-parameters, whether these latent variables. For example, the simplest model to consider is just a general, a simple factor analysis model. So the factor, if the factor is considered a parameter, then here you basically have the likelihood of the dependent variable condition on the factor. A different way to define the DIC is to not consider the factor a parameter, but just to use the model parameters, the loadings of the factor, just those to be included in the theta vector. And in that case, you're going to use the likelihood here, you're going to use the model implied variance covariance matrix to define the likelihood for y. And so these are two completely different definitions. You get completely different numbers. And in order to be able to compare models using the DIC, you have to actually use the same definition for the theta parameters. So essentially, the latent variables in the model have to be the same. Although there's certain exceptions, so latent variables with zero variances, they have double interpretation. They can either be interpreted as a fixed parameter or as a latent variable. So depending on, they allow you, you have this flexibility to actually be able to use DIC to compare models with random effects. So a two-level model with a random effect can be compared using DIC for a model with a fixed effect. So replacing a random effect with a fixed effect can be done with the DIC. So here's a list of actually the DSEM specific. So what exactly actually goes into that theta parameter of unknown quantities? So basically these are all the random effects from the two between levels. So the random intercepts, the random slopes. And those two are also for standard two-level models. And pretty much in any software that you use, those will be inside that theta vector. These three rows actually are specific to the DSEM estimation. So initial conditions are generally considered are in the theta parameter, in the theta vector, and also latent variables that have lagged versions in the model, and also missing variables for dependent variables that are lagged in the that you use lagged versions in the model. So those two rows are actually they can produce a substantial amount of missing quantities that goes into the theta vector, and they generally make the DIC actually more difficult to use. So what happens is, because of this, these known quantities are individual time specific, there are a vast amount of them. So if you have a latent variable and you have 100 observations with 100 time points for each observation, then you end up with 10,000 latent variables on the within level that will be considered known quantities. And when you actually compute the DSE, what happens is that all these unknown quantities have to be integrated. So it takes a long time for the DSE to actually converge. So it's very common situation that your model will be estimated very fast. You can get the model estimates to converge in a few hundred iterations, but actually to get a stable DIC estimate, you might actually have to iterate a long time, and I'll actually show you an example later on of that. So this actually, so the reason we actually have this block, all these quantities here, is to make the computation of the deviance very easy and fast. So we iterate for each MCMC iteration, we have to compute that, and we don't really want to have this be very complicated. And so that's why we have a longer list of elements in the theta vector. Ellen has been a big proponent of actually trying to actually get DIC to work for more and more models and be easy to estimate. So I think we've tried to fight back, but I think we're kind of giving up at this point. So we've actually going to, in the next version, we're probably going to try to remove these two rows that are actually making this DIC estimation particularly difficult. It is possible, but essentially what we have to do is do a maximum likelihood estimation for each MCMC iteration, something we really try to avoid to do, because if you actually end up doing the ML within each MCMC iteration, it could actually slow things down quite a bit, but we'll give it a try, and if it works out, that might actually change for the next version. One thing to monitor when you're using the DIC is always to monitor the estimated number of parameters, the PD. Again, that is supposed to generally be close to the number of elements in this vector. So you can kind of make sure by looking at the PD, you can kind of make sure that it matches your understanding of what the unknown quantities are. So generally, it's not going to be the precise match because when some of these random effects are highly correlated, if you have two random effects that are highly correlated, they do not count as two parameters, but they'll more count as almost one parameter, 1.5 or something like that. So there is a reduction in the Bayesian estimation. A parameter doesn't. So it's an estimated number of parameters. So it's not an actual integer value. It can be reduced, and it is reduced particularly when random effects or the parameters are highly correlated. And again, when PD is large, you have to expect that the convergence of the DIC is going to be slow, and you need to make sure that you have enough iterations to get a stable estimate. Even if you don't have a stable estimate, in most cases, you'll be able to use to compare models, because the differences between the DICs will be large enough that you won't need a very precise estimation. But in certain cases, you will probably need to run very long MCMC sequences to get stable estimates of the DIC. So the next method that we recommend for model fit evaluation is based on comparing sample and model estimated statistics. Assuming stationarity of the autoregressive part of the DSEM model, we can compute subject-specific model estimated means, variances, autocorrelations of log L, and those can be compared to the sample counterparts. One caution about this is that the meaning of this stationarity is that when we estimate the means and the variances, we use a method that assumes stationarity of the model. It assumes stationarity of the autoregressive part of the model. If you have a trend in the model, then this estimated if you have a trend in the autoregressive part of the model, the estimated means and covariances can be incorrect. And I'll show you an example of that later. So the only thing to the thing one thing to remember is that those output options that depend on the stationarity assumptions. These are the residual output, the Tech4 output, and the standardized estimates, and those will assume stationarity of the autoregressive part of the model. There's a way to deal with that. Either you can use residual DSEM style models such as the mirror model, which basically extracts the trend in the data from the autoregressive part, and that will keep the autoregressive part be stationary. And I'll give an example later on, so don't worry about this point. So once you actually have model estimated quantities for each individual, you can compute such things as the correlation between, so this is the model estimated mean, and this is basically the sample mean for each individual. And you can compute the correlation between these statistics across individuals. You can also compute the mean squared error. The correlation is actually available and it's computed for you in the Mplus plot utilities. The mean squared error, you have to save these things and compute it separately. You can save this from the plot menu. I'll show you that later. Model estimated autocorrelations are also available. They're not available in the plot utilities, but they're available in the residual output. And the other thing to remember here is that when you use sample quantities, sample quantities are not very reliable when you have missing data. So the model estimated quantities can actually be accurate, and the sample quantities might not match the estimated quantities just because the data is not missing completely at random. But if the data is missing at random, the sample quantities actually might be inaccurate. So because you have the missing data, and so in such situations, you have to be a little take these kind of model fit evaluations with just be cautious about the missing data situations. So how do we actually estimate the model estimated means and variances in time series in the DSEM framework? So there's two parts to that estimation. There's the part that deals with the time series portion of the model, and then there's the part that deals with the structural part of the model. And the structural part of the model is just what you do with standard structural in SEM models, basically. So I don't have that on the slide here, but it's the standard method. What happens in the time series portion of the model? So I've just written here a simple time series equation. And if you assume stationarity, then the mean of that variable zt is also the same as the mean of the zt variable in the previous L periods. And so you can, if you take the expectation of this equation, you can actually solve the equation in terms of the expected value of zt. And this is, of course, a very simple solution. It looks like that. And so for the variance-covariance, the situation is slightly more complicated. And we use these Euler-Walker equations, which are basically written here. But they essentially use the same approach. So you assume that the covariance between zt and the prior version of z is independent of the time. It only depends on the lag between the two variables. And so if you have this kind of an invariance, you can use these Euler-Walker equations to compute these quantities. And again, remember that this method actually assumes stationarity. It's interesting thing that to note here that the Euler-Walker equations actually they date back in the 1960s, and those were actually used to actually do the model estimation. So you would actually estimate the sample autocorrelation matrices, and then from there you would estimate from this equation you can actually estimate the model parameters. But now we do the opposite. We get the model parameters from the MCMC estimation, and we produce the model estimated variance-covariance matrices. Okay, so next topic is centering. I'll just show you a little simulation study that will describe the value of the Mplus approach. So we're going to use a two-level random autoregressive AR1 model. And the Mplus latent centering model looks like that. So we have a latent mean here, and we're regressing on the y variable at the previous time point. And the variable is the mean of the y variable is subtracted. So this mu I basically in the prior notation, that was basically the yi2, so it's the between portion of the variable. So this is what the Mplus latent centering looks like. In the past, because estimating such model was not possible, what people used to do is basically they would replace this latent mean with the observed mean using the sample mean for that variable, and produce this quantity, the centered quantity. And then you can actually use a standard two-level model to estimate this equation. So this is what we call the observed centering. And then another model we're going to compare here is the uncentered model. So basically, we not center this covariate at all. We have using this observed centering actually yields biases, and we've seen that actually also in two-level models. So these are some papers that actually describe this bias. So in the two-level AR model, the bias actually occurs in the mean of the autoregressive parameter. The autocorrelation bias is described in this paper by Nickel from 1981, and a more recent paper by Hamaker and Grassman. This similar bias actually occurs also in two-level models in the framework of big fish, small pond effect. And here's a paper by Lutke that actually, in psychological method, that described that bias. And we have also one of our web notes is dedicated on that. And the bias basically occurs because of this phenomena where we actually replace, instead of using the true mean here, we actually use the sample mean. And the sample mean has a measurement error, and when you do that, the measurement error is not accounted for. So in the big fish small pond effect, the bias actually occurs. You have basically in that model you have just a simple path analysis model. You have regression on the within level and regression on the between level, and the bias actually occurs on the between level regression parameter, and this is basically what the bias looks like. Nickel's bias again occurs for the mean of the autoregressive parameter, and the bias looks like that. This is just a formula that approximates the bias that you're going to get when you use the observed centering. And both stem from the fact that you use the sample mean instead of the actual true mean, which is unknown. Both of these biases clearly disappear when t increases. As t increases, both here t is in the denominator and here it's in the denominator, so the bias becomes near zero as for large t, for large cluster sample sizes. And both biases can actually occur in the same example. This actually is a little, for us it's not, again, I mentioned yesterday, that was never our goal, to actually resolve Nickel's bias. This method actually doesn't really exist when you have missing data. So it doesn't really, this exercise where I'm going to show you that the latent centering is a good idea, is a little really practical importance for the very simple fact that these other two methods really don't exist in the most general framework. And in case you have missing data, you can't actually do this because you have not only that the sample mean is going to be could be misestimated, but also the fact is that when you have missing data, this is still a known quantity. So when you don't have the predictor, you can actually have this equation. So the other two approaches don't really exist when you have missing data. Another interesting thing to note is that the uncentered method that was pointed in that paper by Hammaker and Grassman is that this uncentered method actually resolved Nickel's bias. It also, the autoregressive parameter, the mean of the autoregressive parameter is consistent. So there's no bias using the uncentered method. However, the uncentered method yields biases in other parameters. So the one place that you actually will screw up using the uncentered method is you're going to misestimate the intra-class correlation, because now you've put in part of the between portion of the variable in the within level equation, and that's going to generally reduce the variance of the estimated intercept. So we don't really consider that as a solution to really anything. Another interesting thing that was reported in Hammaker and Grassman is that even if you actually center, it's not just simple issue about not centering with the correct mean. So they actually, in a simulation study, you can actually center here with the actual mean because you would know it. And they still got the bias, Nickel's bias. And the reason, again, is that, with the true equation, you have an uncertainty in the predictor that would not be reflected when you provide an actual observed predictor with any kind of centering. So here's a little simulation study that shows that the Mplus method works quite well, and we vary here the number of time points and the number of individuals in the sample for this two-level AR1 model. So these are the biases that are produced by the latent centering model. It's very small. Here the observed centering bias is quite large. And also here's this Nickel's formula that I showed you here. It appears that Nickel's formula predicts that bias quite well. So it predicts the actual bias really closely. So this simulation illustrates that latent centering eliminates that bias. And here's what happens with the uncentered method. So here we're comparing the bias that's produced by the method for the variance of the random intercept, and the latent centering produces much smaller bias than the uncentered method. So basically, there's some bias here, but that basically is a function of the number of points in the data. So the bias will disappear asymptotically as the number of individuals increases. Or you can use weakly informative priors actually to tinker with this basically small sample size bias. But for the uncentered method, that bias will not disappear. So in our discussion, Ellen came back and said, well, this is not a correct comparison. And so we had to go a little deeper, further here. And so if you just look at the Mplus centering method, so what happens here if, so here's again the equation, and we're going to basically expand the brackets here, and you can rewrite that same equation, and the intercept basically becomes mu I times 1 minus Ri, where Ri is the autoregressive parameter. And here's the uncentered model, and you can see that these models are virtually identical, except for the fact that this mu I is now mu I multiplied by 1 minus the autoregressive parameter. And so the model is actually the same in this particular situation. And you can say, well, we can just estimate the uncentered method, and I can just divide the intercept by 1 minus the autoregressive parameter. And this way, I'll get the correct estimates for the intercept, and I can, from there, I can get the correct variance. So one of the advantages of the Mplus latent centering is that you don't have to do that. You don't have to go through this additional transformation, and it's done automatically for you. But then the other advantage is the fact that that doesn't really generalize. So this sort of a transformational approach doesn't really generalize. So I'll just show you this with a simple example. So we slightly complicate the model now that it's not just a simple AR1 autoregressive parameter, but I'm going to add a covariate on the between level. So if you add a covariate on the between level, now we have this. This is basically the portion of the variable that's the between portion of the variable. So this is a time invariant covariate. So you have mu I plus beta x, and that's also used here in the centering of the covariate. And if you do the same thing that you expand the brackets here, what you get is again this random intercept is multiplied by 1 minus the autoregressive coefficient, and the coefficient in front of the covariate, the time invariant covariate, is now beta times 1 minus Ri. And you have again this the autoregressive coefficient regressed on now the uncentered value of the dependent variable. And now let's compare this to the uncentered version. Looks very similar. We can say the same thing. We can divide the random intercept by 1 minus Ri. Problem is now here this quantity is random, and here it's fixed. So you can't actually do this transformation. It's not the same model. If you try to, it basically doesn't work. That transformation won't work anymore. And in fact, it's not even identified. You can make it a random, but it's not even identified. So the only way it's identified here is because there's a high correlation between this and that random part. So anyway, the uncentered method doesn't really apply for more general models. So the next topic is the mere one model, the mere measurement error autoregressive model. Bengt explained this yesterday. The ARMA 1-1 model, so the measurement error autoregressive model is this model where you have a single indicator for a factor at time t, for a factor, and and then you have an autoregressive equation for that factor. So so it's a single indicator model, something that's not identified in general in standard SEM, but in this in this time series modeling, it's actually identified. Not only it's identified, it's basically equivalent to the most popular model in econometrics. Well, I mean, this is one of the most fundamental models in econometrics. So here's the ARMA 1-1 model. So it's you have mu, you're regressing this on the previous version of the that variable. So this is the AR part of the model. And then you have the residual, and you also have a regression on the previous version of the residual. And this model has 4 parameters: mu, phi, this parameter theta, and the variance of the residual. The measurement error model also has 4 parameters: mu and phi. And then you have the residual, the variance of the residual here, and the variance of the residual here. So so the 2 models are equivalent, and you can obtain the mere 1 parameters from the ARMA 1-1 parameters using these 2 equations. You can do that as long as those 2 equations produce positive variances. So it turns out that the parameter space of the ARMA 1-1 model is a little bigger than the parameter space for the mere 1 model. So it's not a 1-to-1 correspondence. This is slightly bigger. But generally speaking, in the data that we'll be interested in, this is this correspondence works well. One thing to note here is that the autocorrelation for the factor is always greater than the autocorrelation for the observed variable. So that's kind of a sort of a natural feature of this measurement error model, and you can once you start estimating these models, you will always have that the autoregressive parameter for the factor will be greater than the autocorrelation for the observed variable. And this model actually again shows that traditional SEM logic does not really hold well it doesn't hold in the DSEM framework. So one indicator factor model is perfectly identified. There's 2 reasons to prefer the mere 1 model versus the ARMA 1-1 model. So we have in Mplus, it's a more efficient estimation for that model. The ARMA 1-1 model, as Bengt showed you yesterday, requires fixing of residuals to 0. You basically have to set up these residuals as factors, and then in addition to that, you have to introduce another factor with 0 variance. So the Mplus estimation of the mere 1 model is more efficient. The mere 1 model also, it's easier to interpret from a SEM perspective. So you have just measurement error, it's standard measurement error interpretations. there's two reasons to prefer the MIR1 model against the AR1 model. So the MIR model actually has more flexible. The AR1 model has an exponential decay of the autocorrelation. So if you have, so the autocorrelation, so here's an example. So the autocorrelation function for the AR1 model, it kind of goes very rapidly down. And so it's somewhat unrealistic. Between the time periods, it goes quite quickly down because it's an exponential function. And for the MIR1 models and the ARMA11 model actually does not go exponentially down. So it can linger on for much longer. And essentially, it has two parameters. It's a two-parameter function that matches the estimated autocorrelation against the observed autocorrelation function. So, but the reason actually I got obsessed with the MIR1 model is because it actually resolves so many issues, other issues. So there's actually not on this list, but you know, we're going to see further on examples. So advantages of the MIR1 model. So it resolves the issue about categorical data. So you can actually use time series modeling with categorical data as long as you stay in the MIR framework. It resolves issues with covariates. So you can easily separate the covariate from the autoregressive part. It resolves these issues that I mentioned earlier with the stationarity of the model. You can easily transfer the trend in the model from outside of the autoregressive part of the model. So it's actually a framework that we use now all the time. So and you'll see all these examples in a minute. And it's very easy also to test the MIR1 model versus the autoregressive AR1 model. You simply have to test that this variance here is significant. So here's a little simulation actually to put you in the right framework of mind when you think about these models. You know, how easy is it to estimate an ARMA11 model and a MIR1 model? And this table is actually obtained in Mplus using the MIR1 model, so it's the most efficient estimation that we have available. And here are basically the four parameters in this simulation study, and we're going to use sample size of, so this is a single level model, n equals 1. We're going to use sample size of 100, 200, 300, and 500. And you can see that even with 100, you know, there's some bias in these parameter estimates. So keep this in mind that this is actually the MIR1 model has it's not super straightforward to estimate. So it has these biases that you know, even you can see them in for 200 for sample size 200. They're still there, although the standard errors actually now recovered. So the confidence interval gives proper coverage. So generally, to estimate an ARMA11 model, if you talk to econometricians, they would generally recommend at least 100 and more like 200 time points to get good parameter estimates. Now, luckily for two-level models, which is most of our interest is for two-level models, this requirement for the time is actually is not needed because of the fact that we're not generally going to estimate those as individual specific for each cluster. So in a typical application, some of these parameters are going to be random and they're going to be cluster specific, but not all four of them. And the fact that some of the parameters are going to be invariant across the clusters allows you to carry information from one cluster to another, and therefore would allow you to reduce the demand for the number of time points in the estimation. And you would basically, you'll be able to get good parameter estimates even with 50 time points, and probably even less. Here's a little simulation study for ARMA21 model. So here's the ARMA21 model. It's kind of the ARMA11 model, except now you the autoregressive part you can regress not just on the y from these previous time points, but also from the 2 periods back. And you also have this moving average part of the model. So regressing on, of course, the residuals here, and regressing also on the previous residual. So here's how you actually specify this in Mplus. This now is dealt with as a factor. So you basically use this to define this factor. And further on, you regress the y variable on the previous version of that factor. So this parameter is right here, and this is basically the autoregressive part of the model. And again, this is the one problematic issue here, is that you have to still further introduce a residual and then fix that residual to 0. And that's in the model of Monte Carlo, I can fix that to anything. But in the model statement, if I fix it to this very small value, then I'm going to cause this very slow convergence. So I fix it to 0.01. Let's look at the parameter estimates. In the parameter estimates in this simulation, so I'm using a sample size of 500, and the parameter estimates are quite good, almost no bias anywhere, and the coverage is fairly good. So this is a more complicated model than the ARMA 1.1, and it's still fairly easy to estimate as long as the number of time points is sufficient. So let's see how some of the benefits of the MIR1 model for categorical data. So we're going to be interested in basically actually estimating time series models for categorical data with just one categorical variable. Now, Bengt yesterday showed you, when you have multiple categorical indicators for a factor, that's a much easier situation. But this simulation kind of shows you that what I'm going to talk about here is using time series models with just one categorical variable. So univariate, and this actually turns out to be harder because with one categorical variable, you cannot measure, of course, the latent variable very well. It's a more unstable measurement model, but it's still possible to do that via the MIR1 framework. So if you have a single binary variable, the MIR1 model basically will be this. So this will be the between random intercept, and you have also this factor that's measured by the y star variable, by the underlying continuous variable, and then essentially you have the residual that's fixed to 1. And then this factor has its own autoregressive equation, and because of this equation, essentially you're building a model, a time series model for that binary variable. And with ordered polynomous variables, the same thing happens. You just have slightly different, the probability of this ordered polynomous variable being in a categories than just the difference between these probit functions evaluated at the different threshold values. But essentially, you have again the random intercept from the between level, and then you have this factor that essentially we're using from the MIR1 model that's measured by the underlying continuous variable of the y. And then you have this, again, the autoregressive equation that actually is the essence of the time series model for the ordered polynomous variable. Just a couple of simulations here. So, I was interested to see what is the demand of the sample size here. And so what I found is that with binary variable, I needed 300 points to actually reduce the bias to get unbiased estimates. And now the coverage is a little low for these two parameters here, but if you run a much longer sequence, you'll probably be able to resolve this. Anyway, this simulation shows that even with just a single binary variable, you can actually estimate using the DSEM framework and this MIR1 setup. You can use a time series model for a single binary variable. Binary variables are somewhat tricky because, essentially the information is being extracted every time there is a change from 0 to 1. And those changes have to be fairly often to provide some information for all these latent variables and parameters. So again, that works much better when you have more than one binary variable. You have multiple indicators for the same factor, and the factor is measured better. Or you can use ordered polynomous. When I redid that simulation with ordered polynomous variables, so I was able to, the demand on the time series is much smaller, so I was able to get good parameter estimates with 100 individuals measured at 100 time points. And you can see here the parameter estimates are fairly unbiased and the coverage is fairly good. Again, some low coverage here probably can be resolved by running a much longer times MCMC sequence to get a more full posterior distribution. So I'm getting to the last topic. And this topic is the adding covariates in the DSEM framework, and we're going to also discuss the new residual DSEM model. So we start with, we're going to use the MIR1 model as it allows us to kind of more fully explore this issue about how to add the covariates in the DSEM framework. So we are going to, but similar arguments apply also to the AR1 model, but it's a little easier to work with the MIR1 model. So there's 3 separate models, actually. There's 3 different ways you can add a covariate in this framework. So here is what we call the residual AR model. And again, without this thing, that was basically just the MIR1 model. So you have a factor, you have the observed variable measuring a factor, and then the factor has an autoregressive equation, which is the MIR1 model. Now we are adding a covariate in the first equation, so which is basically adding the covariate outside of the autoregressive process. You can also do this, we call this second model, which is called the full AR model. We can actually add the covariate in the autoregressive portion of the model. So you can see it's in the second equation, or you can do both. You can actually do what we call the joint effect model. You can add the covariate, the same covariate here and here. You know, it's another, again, you know, example of how the standard SEM logic does not apply to the DSEM modeling framework. Of course, this is not possible to do in standard SEM models. You know, I mean, you have just one indicator here. You cannot identify both 2 regression coefficients if you just have one variable. It's just one, but you know, okay. So the reason actually this thing, the reason this logic actually, the SEM logic fails here is because you know, the SEM logic is based on sample mean and variances. This does not apply in time series models because you know, sample mean and variance are not sufficient statistics, and so they don't explain. There's a lot more to the model than sample mean and variances. Okay, so these are the 3 models, and just to understand a little bit about how they differ, we're going to consider the implications for the expected value of the dependent variable given the covariate. In the residual AR model, the expression is very simple. And so here's the expression. So the mean of this process is 0. So the expected value of y given the x is just the standard. The expected value of this is 0 and this is 0. And you can just get mu plus beta xt. So it's very simple. And that's kind of the appeal of this residual AR1 model. So this conditional expectation resembles much more the standard regression model. So it's very easy to interpret. But what you can notice here is that the value, the conditional expectation, is affected only by the covariate at the current period. It's only affected by the covariate at the current period. And that does not happen for the full AR1 model. So you have sort of an accumulation effect of these covariates. So the conditional expectation of the dependent variable given the covariate is this infinite sum here, and it shows that not just the covariate at the current period affects your value, but also from the previous period. So whatever happened in the previous period also affects your the expected value of this period, and so on. So because this is the autoregressive parameter to this power, this actually converges to 0. The autoregressive parameter is smaller than 1, and so this has a diminishing effect. The covariate values from the previous periods have a diminishing effect on the current period. However, again, this is an accumulated effect. So whatever happens in the previous periods can have an effect on the dependent variable at this current period. And finally, the joint effect model has both of these. So it has the direct effect, and it also has this accumulated effect. So this is the general picture. However, we kind of got, as we kind of worked our way through this modeling, actually, we started first considering this very simple case of when the covariate is actually the time, which is basically the linear growth model. And Ellen has a paper on that, which we really like, and that shows that the residual AR1 model and the full AR1 model are actually equivalent to each other. And when they're equivalent, that means that the two reparameterization of each other, and you cannot, one regression effect is equivalent to the other regression effect, and therefore you cannot identify both of these effects at the same time, which makes the joint model not identified. So let's just dig in here. So the residual AR1 model, the linear growth AR1 model, basically, it can be expressed like this. So you've got the linear trend over here, and then you have the residual, and you have an autoregressive equation for the residual. So I switch back to this to the AR1 framework here for a minute. So the full AR1 model. So again, the trend here is actually outside of the autoregressive equation. Now the full AR1 model, the trend is within the autoregressive equation. And note here that the effect of time here is direct. You know, you have just this coefficient. That's how the time affects yt. But here, it's not just this, but t is actually inside yt minus 1 as well because of this equation. So the effect of time is a little more complicated. It comes from this portion as well as this. So it's a combination of this. It turns out that, again, these two models are completely algebraically equivalent. And these equations, actually, the simple equations actually will show you how to derive one set of parameters with the other. And one thing to note here is that you know, the growth term is a simple division. So to obtain this, the slope term is basically a simple division, and you divide by 1 minus the autoregressive parameter. And that also actually happens for, but the mean here is not as simple, it's more complicated. So at some point we kind of thought, well, perhaps this actually happens for all the covariates. And we fooled ourselves, and you know, for about a month almost, we kind of thought that this is like just not an issue. Until we started seeing enough evidence that it is an issue. But anyway, so I worked through the quadratic growth model. So again, we have in the quadratic growth model, you have again the residual AR1 model. Basically, you have the quadratic trend, and then you have the autoregressive equation for the residual, and then you have the full AR1 model with a quadratic trend, where the equation has the quadratic trend within the autoregressive part of the model. And so it turns out that, again, these two models are algebraically equivalent, but the equations are not different. So you can obtain the parameters for the residual AR1 model through these equations using the parameters of the full AR1 model through these equations. And what you can see here is that the quadratic term now has this relationship that this coefficient satisfies this relationship that you can just obtain gamma 2 from beta 2 by just simply dividing by 1 minus the autoregressive parameter. But the relationship for the linear trend now changes. So it's no longer that simple, it's no longer this term, but it's something more complicated. So that's kind of an evidence that, you know, obviously, you know, things are more complicated than we thought. So we went back to this model and we try and see if it's really identified. So this is what I'm going to show you here. It's a little simulation where we're going to we're going to generate data from the joint model, and we're going to estimate it with the full model and also the residual model. And so again, this is, you know, the covariate actually, and this is in a two-level framework. So we have the residual, we have the effect of the covariate is outside of the autoregressive equation, but it's also inside. So we have the two regression coefficients, and beta 1 is 0.3, beta 2 is 0.4. And we generate this covariate, you know, of course, it's important to figure out how to generate the covariate. So we generate it from an AR1 process, and we vary the autoregressive coefficient for that generation process. So when you have Rx equals 0, the covariates are independent of each other. And as you approach, you know, you can increase this Rx to, you know, if your Rx converges to 1, then the covariate becomes a lot more like the time variable. So anyway, so we will generate data according to the full joint model, the joint model, and then we're going to analyze this with the residual AR and the full AR. And here are the results of the joint, analyzing the data with the joint model, and you can see that in all the cases, the parameter estimates are estimated very well, and the coverage is quite good. And so that what the conclusion here is that this model is well identified. And so for general covariate time specific covariate, you can add the covariate in both places, inside the autoregressive equation and outside. So when we analyze the model with the residual AR, then we have just basically we estimate the model excluding this term, excluding that term. So there technically is no true value for beta 1. I sort of will say, well, we can maybe assume that the true value is 0.7, but there is no true value for that parameter. But the results clearly indicate, as you can see here in the phi parameter, is that the parameter estimates are biased, and it's depending on the actual parameters you use in the simulation, that bias can get in very bad. Basically, it just happened here that it looks a little bit small, but it's actually depending on these the generating model, whether it's closer to the residual or the full AR model, you can get these biases to be either big or small. So it's not that this bias is always looking small. So anyway, the beta coefficients, of course, is misestimated. So it's just all over the place essentially, and also the autoregressive parameter is misestimated as well. And the same thing happens when you do when you analyze the data with the full AR model, which is basically trying to put the covariate effect only in the autoregressive, so without this effect. And again, we have the same problem that there's no clear definition of what beta 2 would be. But if you assume that beta 2 should be just the sum of the two betas, you again clearly see that the parameter estimates can be the parameter estimates are biased, and also the autoregressive coefficient is also biased. So the conclusion of this little simulation is that there is, in general, for a general covariate, except when the covariate is the time variable or the time variable and the time variable squared, as in the quadratic model, or generally the general polynomial of the time variable. Except in that case, for all other residuals, the residual AR model and the full AR models are not a reparameterization of each other, and you can have this option of, you have this question of where to put the covariate. We are sort of arguing that, we're coming sort of new to this field, and so, personally, I don't care about tradition and, like what other people have been done in the last 50 years. I don't think that, this question of where to put the covariate should actually depend on what has been previously published in the literature. I think, the only thing that should decide this is the data itself. And so, and you can actually have, in general, it's very easy to test in which equation the covariate should be. You can put it in both equations, estimate it, and see which of the two parameters is significant. And actually, yesterday, Bengt showed you an example where the DIC clearly indicated that the placement of the covariate was better in certain situations. It would be better to be within the autoregressive part of the model. One other thing to note here is that because I use the MIR1 model because it does have this flexibility of having the two equations with two separate residuals, and I can do this more easily where I can place the covariate in or outside of the autoregressive equation. But in the AR1 model, that is a problem because you don't have these two residuals, and so separating the two equations it will be separating the two regressive parameters is difficult, and you have to create this residual and then fix it to 0. So, and this is basically the reason why we are started being interested in the residual DSEM model, is because this fixing of the residual is causing slow convergence, and it's to be able to estimate the residual AR1 model. The perfect framework is to actually use the residual DSEM framework model that I showed you, the general definition that I showed you earlier, which kind of extracts the structural equations separates the structural equations from the autoregressive part of the model. So anyway, the DSEM model will absorb this complexity when it's available. That DSEM framework is really where you want to estimate the residual AR1 model. Let's see, how are we doing with the time? It's 10, so...
You can take another 10 minutes.
Okay, sounds good. So here's another simulation where I'm going to illustrate this point about, you can estimate again this, the residual, you can separate the, you can estimate the residual AR1 model in version 8 without the DSEM framework, which will come in the next version, using the MIR1 model and fixing the residual variance to 0. So what I'm going to do here is basically generate a 2-level data with 50 points for the time series, and then with 50 individuals, just 50 replications in this simulation. And we're going to use a covariate coming from an AR1 model with autoregressive parameter 0.5, and we're going to use AR1 model, and the covariate is again outside of the autoregressive equation. So how do you actually estimate? How can you estimate this model how do you estimate this model? So there's 3 ways to estimate it. You can do it with the DSEM model, which is basically here. This is the model input. So the y on x here is basically this equation, and then you have the autoregressive equation is basically here on the within level. And that, again, y hat basically represents the residual of y. So this variable here. So this is basically the DSEM language. And also you can, you can basically also estimate this model using the MIR1 model, using the DSEM framework, converting this residual to a factor, and then adding another residual here that's fixed to 0. So there's 2 ways to do it. You can fix the residual variance to 0, or you can actually estimate that residual variance without fixing it to 0. So it generally will be estimated to a small value that's close to 0. So there are basically 2 DSEM MIR1 approaches to estimate that model, either with fixed variance to a small value, or just let the variance be free and let it be estimated to a small value. And here are the results of this simulation. So the DSEM framework, so it's like this is the number of seconds that it takes per replication to estimate this model, and you can see the residual DSEM method actually uses just half a second per replication, so it's very fast. It only uses 200 MCMC iterations until convergence. The DSEM with free small residual variance actually takes the longest here, so it's 30 seconds, and if you fix it, it's 3 seconds. There's no bias in the parameter estimates, so the bias is fairly small, and the coverage, you can probably improve the coverage to some levels here by running it much longer, but I think they already run pretty long here, so the coverage is a little subpar here. It is possible to estimate it, but again, the most optimal way to estimate this kind of model with the residual AR1 model would be through the DSEM framework. So, final example, and so in this example, I'm going to illustrate 8 concepts. So I was really happy that a single example can illustrate so many different concepts. So let's go through the 8 concepts that we're going to illustrate here. So it's a very simple model. So it's the linear growth AR1 model. So we're going to show what Alan's Hammaker paper was about, the equivalence of the residual and the full AR1 models for the linear growth model. We're going to illustrate that the model estimation is correct even when the stationarity is not present in the model. and that only the residual and the tech4 and the standardized output depend on the stationarity assumption. So these are basically all the outputs in Mplus that depend on the Euler-Walker equations, which do assume stationarity. But we're going to illustrate that the model estimation, even though the model is not stationary, the model estimation of the DSEM framework is correct. And then we're going to show that indeed when the autoregressive portion of the model is non-stationary, that the Euler-Walker output actually is incorrect. We're also going to show in this little example how the mirror concept actually allows you to separate the trend from the autoregressive portion. And we illustrate here the advantages of the residual DSEM. We also illustrate the challenges in the Bayesian framework when you fix a small residual variance to zero. And we're going to show that there's 4 different ways to actually run the same model and get the exact same parameter estimates. And also, final concept that we illustrate here is the fact that model constraints can be used to implement the reparameterization of the residual on the full AR1 models. So here is the linear growth model. So we're going to generate 500 points using the full linear growth model. So the autoregressive equation here includes also the trend. And here's some parameters that are used for this simulation, and basically use time 0.1, 0.2, just so that I don't have to, because they're 500 points. If I use from 1 to 500, then the Bayer coefficient has to be really small here. So instead, I use this time point 0.1, 0.2, etc. So we generate data like that, and we're going to estimate the model using in 4 different ways. So this is basically the same way that we generate the data using the full AR1 model that estimates one equation where the trend is inside the autoregressive equation. Then we're going to use the RDSEM Mplus developmental version for estimating the RDSEM model, where the linear trend is outside of the autoregressive equation. And then we're going to also use the MIR1 modeling framework, where we've got the linear trend over here outside of the autoregressive equation. And we have the autoregressive equation again. To actually make this model equivalent to this, all we need to do is fix, let's see, what do we fix here? We fix, let's see. Well, I mean, this model is the same as this model as long as I fix this residual variance to 0. It's just the factors are, the factor f here becomes this residual variance. So when this is fixed to 0, then you get this model is equivalent to the residual AR1 model. And then the final 4th model is when instead of fixing it to 0, I let that variance be a free parameter. So here's the model input for the 4 methods. So this is the full AR1 model input. So you've got the lag command, and then you have the y on 1, y at 1. And these are basically the model constraint equations that convert the full AR1 parameters to the residual AR1 parameters, and those are the ones I showed you on the earlier slide and from Ellen's paper. So basically, you can estimate the residual AR1 model. You can get the residual AR1 model estimates using the model constraint equations. Here is the Mplus 8.1 version. So again, you have the new notations for the residual. So the y hat, I regressed on the y hat from the previous time point. So the residual autoregressive equation, and then the trend is separated from the autoregressive equation. So this is the RDSEM model estimation. And we have now the MIR1 model estimation. So how do you do this? So we have we define this factor that's with a single indicator factor, and we regress. We put the autoregressive part of the model on that factor, and the y is regressed on the time variable. And so that so you can either fix that residual variance to 0 or to small value, or just let it be estimated. And here the results. So in terms of speed, the two that have optimal speed are the DSEM with the full AR1 model. So the first and the second basically provide fast convergence. Those with the small residual variance are slow. The model parameter estimates are pretty much identical across the 4 different methods of estimation, except in those that use the small residual variance, because I fixed it to 0.05, and so they kind of affect these residual variances. But the autoregressive parameters and the growth model parameters are quite close to the other model estimations. Here's what I also looked at is the estimates from Mplus about the estimated model means and variances. And here the sample quantities. And you can see that these 3 methods basically for which the assumption of stationarity of the autoregressive part of the model, those actually produce correct values and they match the sample values. And the one model that does not satisfy the condition of stationarity of the autoregressive part of the model, because the trend is inside the autoregressive equation. So those actually outputs from Mplus will be incorrect because it does violate the stationarity assumption. And the final thing is the DIC, and the DIC between these 2 models, they match fairly closely. And the DIC for these 2 models, they are not applicable because you have these residuals that are near 0, and basically the deviance is actually minus infinity. So those DIC quantities do not apply, but the DIC here agrees. So there you go. So these are the 8 concepts that I wanted to illustrate with this very simple example. So hopefully that cleared some of the intricacies of the DSEM framework. So yeah, I'm gonna stop here, and if you guys have any questions.
Okay, thanks a lot, Timur. So you can see that the insides of Mplus version 8 contains quite complex statistics. So we're doing the peaking on the difficulty level according to the chi-square distribution. It peaks very early today. So after this, everything will be much easier to digest. And you can also see why Timur's PhD actually was in mathematics at Caltech. And you can see why Timur, when participating in an international competition in mathematics in high school, won. That was in China, was it?
Yeah.
So with that, any questions? You want to quibble with some formulas?
Definitely not quibbling with formulas, but question I had about the latent centering. If the mean for each person, if that distribution is not normal, really skewed, is the latent mean then going to be biased, the latent centering?
So I think, are you presenting something on that or no?
Not exactly that.
So generally speaking, when the size of the time series is sufficiently large, the assumption of normality, which is essentially the between level model, that's your assumption of normality is the, so the between level model essentially you can view as being the prior for that autoregressive, for the mean. And as long as the time series is, say 50 time points, then this between level model has a fairly small influence on the estimate of the mean. So it's
I'm just curious, say I had like a daily diary study for, say I've got 25 days and I've got like something like suicidal ideation, which is pretty skewed. Would then you think it might be a problem?
If I can add to that, I'm going to talk about that this afternoon, and I would say that that might be on the limit of what could be a problem if it's very skew. But we saw that for very skew distributions of the autoregressive coefficient, for example, time points larger than 30 seems to be kind of the point where everything is okay. So depending on how skew it is, 25 might be a problem, might not be a problem, but that's kind of where the limit is, where the border are.
But of course, it assumes that linear models are still relevant, which may not be the case when you have suicidal ideation, because you probably have a strong floor effect, which is an issue. Like we talked about the first day, how to model variables that have that situation.
So yeah, and Nikhil's bias is a little bit of a undeveloped story there. So we talked about Nikhil's bias being the mean of the autoregressive parameter. That's not the whole story. The story is that whatever misestimation of the autoregressive parameter occurs is probably not just a simple shift of the autoregressive parameter. It's probably all over the place. Those simulations that I showed you, they were applicable just for the mean of the autoregressive parameter. There could be like a vast thing going on behind the scenes that if you average things, it will look better than it actually is. If you actually look through the mean squared error between the true autoregressive parameter and the estimated autoregressive parameter, that would actually probably look worse, just because of the fact that it's probably not going to be just a simple shift between the true and the estimated when you use the observed centering. So, but ultimately, I would not worry about the distributions of these random effects. And the reason it is because as the cluster size increases, that assumption about normality of the random effects, which is essentially the between level model, becomes much less important. The data on the within level drives the estimation of the random effect. And so, no, it's not going to affect anything. You can try it in simulations, to convince yourself, because I'm not very convincing. It's kind of, but but this is the reality. It's not, you're not going to find anything. Yeah.
And I will show some simulation studies of that this afternoon as well, so we'll talk more about that.
And I'll show an alternative modeling that tries to take into account that floor effect. All right. Any other questions? Over here? Yeah.
Thank you. I wonder, could you provide some concrete examples of where the DIC criteria could be used to kind of examine the fit of different models, as well as where it falls apart, such as maybe comparing lag 1 versus lag 2 may not work, whereas perhaps adding fixed effects could? Just something concrete might help at least.
So you can DIC, when you can use DIC, so you can use it to, if you want to see if an effect is random or fixed, no problem. You can use the DIC to do that. You can use the DIC to compare models that have different set of fixed parameters. So whether a set of covariates, say, should be included or not, that can be used. And do you want other examples that are cannot be used for? So in contrast, I would say that an example that you cannot use is so if you have a factor analysis model with an autoregressive equation for the factor versus a model that an AR1 model, so each indicator has its own autoregressive equation or a joint, that will not work, because that cannot be used, because the factor, if the factor, whatever factor you have in there, and it has an autoregressive equation, that factor is going to be conditioned on, and so it's going to be completely different likelihood, and it will be easy for you to see it. It's just not, for me, when I say these things, we have to go and say it, so you're not shocked when you find out about it. One way or another, you will find out about it. But actually, the reality is that I personally don't have any problems using DIC. Banked using just Ellen is the problem. So.
Do you want to comment, Ellen?
Don't get me started. No, I think one of the major disappointments for me was when I was running a multi-level model, factor model. Sorry. So the model that I ended with yesterday and that I will talk about later today, I was interested in finding out whether the factor loadings within person were the same as the factor loadings between person. So then I constrained the factor loadings. So I ran two models, one in which there were no constraints and one where there were constraints. And there seemed to be a difference in DIC, but I wanted to make sure that the DIC was stable, so I tried out the same model, but with a different seed, so to the same number of iterations, but just starting with a different seed. And I found differences, so it should be more or less the same. And
right.
I ran like 1 million, or like, no, maybe not 1 million, 500,000 iterations. It took a bit of time, and then the difference in DIC could be like 200 points. And when you look at the rules of thumb that exist for DIC, it is like, okay, 2 points is not a big difference, 6 points is quite some difference, and
right. So these rules don't
is a
apply.
lot.
These rules don't apply here. Yeah, you have to. When you have 10,000 parameters, those rules don't apply. You're going to have to run essentially, unreasonable amount of iterations, so it's not even practical. However, you were able to do your testing. For the reason is that the difference between the two models was much larger than 200. Correct?
No.
No, I think it was correct.
No, so I. No, for me, this was the point where I thought, like, okay, so I still don't really understand when the DIC is comparable and when not. I just admit this, I just don't get it. And I've been trying to get Tiomir to explain it to me, but
so,
I don't get
again,
it. I mean, I understand the general idea, but I don't understand when I'm in one situation and when I'm in the other. Yeah, so, for instance, you are saying an observed AR1 model and an AR1 model with measurement error. Are these comparable?
Oh, say this again?
The observed AR1 model and then what you call the MER model. No,
they're not comparable because one of them has a factor that's conditioned on and the other one doesn't. Well, this is, you can see what's going. You can see.
For me, I just don't understand what he means when he says a factor that's conditioned on.
This is the healthy give and take within this group. That
this we do through email,
After now we sort of have an algorithm. We are sort of ready to get to it to actually get this resolved in 8.1. So you won't have this vast amount of parameters, and then the DIC would be better, easier to use.
But what about models with categorical outcomes? It still is based on maximum likelihood estimation behind the scenes.
Yes. So
and therefore we sort of put DIC aside, and go for some other model comparison.
Yeah, exactly. So in the plan is to actually it was actually in the plan for version 8, but we didn't get to it. But in the plan is actually to have the model test, which is much easier to estimate a hypothesis like this. Just have the model test statement inside the Mplus, and of course it's fairly trivial to do it. You can even do it yourself, outside of the program. But
just to emphasize that's a great idea. We have the command model test, and you use it quite a lot in the ML framework. It doesn't exist yet in the Bayesian framework, but what Tiomir is suggesting is that quite easily, relatively speaking, he can add that to a new version of Mplus, and that will be really an important way to compare model parts.
Yeah.
In the slide 62, the Y star 0.05, are you constraining the variance of the zeta and eta to the 0.05 or variance of zeta only to 0.05?
So that basically is the residual of the Y. So it's this residual right here. And that's basically the residual, that's the extra residual. So we wanted to estimate this model, but we end up estimating this model. We want this actually to be either fixed to 0.
Can I ask you, should this variance be the variance of epsilon, not z?
Yes, that's correct. Yeah, that is a typo here. So that should be that epsilon t. Sorry.
Thank you.